Now that we have learned how to solve some systems by substitution and also using linear differential operators, we're going to press on to matrix methods for solving linear systems of differential equations. In 5.3, we study matrices and linear systems. Your primary goal in this section is to learn how to express a linear system of differential equations using matrix notation. A lot of what we learn in section 5.3 will be reminiscent of what we learned in section 2.2, looking at the principle of superposition, linear independence, and how we know when we have a general solution to a differential equation. We're going to see those same concepts applied to multiple equations at once. Let's begin with the notation. A general system of n first-order differential equations is given by, and notice here we have our system. This is familiar. We looked at this in our last section. And what we want to do is identify independent variable and dependent variables and coefficient functions. So as we saw in the last section, the independent variable is hidden here in the arguments of the function. So let's make a note that the independent variable is t in this case. The dependent variables are numerous, and I can see them sprinkled throughout the equations. Any x with a subscript represents one of the dependent variables of the system. All of those are functions of t, and I can see their first derivatives listed over here in this column. So x sub 1 of t, x sub 2 of t, all the way up to x sub n of t are the dependent variables of the system. The solution to this system is an n-tuple of functions that balance each equation in the system. Now over here in the last column, we've got functions of our independent variable alone, and we're going to see how that, if it's non-zero, makes this a non-homogeneous system. So this is a lot of information in this system, and we're going to condense it down to a single equation. So this system can be written in matrix form as dx over dt equals p of t times x plus f of t. Notice the bold print in this equation. The x that we're talking about here, since it's in bold, represents a vector of solutions. So x of t over here is in bold, and it represents a column vector of dependent variables, x sub 1 of t, x sub 2 of t, on up to x sub n of t. This matrix, p of t, is our coefficient matrix. It contains the functions of t that are the coefficients of those independent variables. And finally, f of t, this is another column vector of functions. Those are our functions of t alone. So once again, this is our coefficient matrix. That's going to be a square matrix. That is n by n. And these two matrices are what we call column vectors. That is, they have n rows and one column. If this f of t equals 0, now notice that's not an ordinary 0 right there. That's a bold print 0. That means we have an n by 1 column vector of zeros. So that represents a matrix of zeros, n by 1, n rows and one column. If this last spot right here is all zeros, then I bet you know where we're going with this. The system is homogeneous. If a function of t alone is part of the equation in any equation, the system is non-homogeneous. Let's understand that the bold print indicates either a matrix or vector. By hand with pencil and paper, we're going to use vector hat on each one of those. So by hand, we would write this as dx with a vector hat over dt equals p of t times x with a vector hat plus f of t. A solution of the matrix equation is a column vector of functions. Notice the bold print here, that would be x of t by hand. This is a column vector, n rows and 1 column. That satisfies the matrix equation. So our solution, we have previously expressed it as an n-tuple of solutions. Now we're going to look at it as a column vector of solutions. So our goal in this section is to understand how to condense a linear system like this into a matrix equation. So in this section, we're just going to be getting to know how to go from system to matrix form and vice versa, and understanding how to express the solution to the system. So in example 1, we have a very important system because we're going to be looking at this particular system all throughout the lesson. So the system x sub 1 prime equals 4x sub 1 plus 2x sub 2, and x sub 2 prime equals negative 3x sub 1 minus x sub 2 is a first-order linear system. The unknowns here, or the dependent variables, are x sub 1 and x sub 2. Please remember that those represent functions of t. It's not an algebraic system where we get an ordered pair of constants that solve the system. We get an ordered pair of functions, or using our new notation, this is going to be a column vector of functions that balance the system. So we want to rewrite this system in matrix form and then as a condensed matrix equation. So we're going to turn the left side into a column vector, x sub 1 and x sub 2 prime equals, now we're going to pick up the coefficients of the system. We're picking up coefficient of x1 in column 1, coefficient of x2 in column 2. That's our coefficient matrix, times x sub 1 and x sub 2. Remember how matrix multiplication works. We don't have a whole lot of background in linear algebra for this class like we used to. It's no longer a prerequisite for this class. So there may be a few things you need to learn about matrices. First of all, let's look at size. On the left side, we have 2 rows and 1 column. So that's a 2 by 1 matrix. On the right side, we have a 2 by 2 matrix, and we're multiplying it by a 2 by 1. Remember, rows are first, columns are second. When you multiply matrices, you can predict the size of the product by noticing first, these two must always match. They must be equal. And when they do match, the multiplication is defined, and the result is a 2 by 1 matrix. So on the left side, we have a 2 by 1 matrix. On the right side, we have a 2 by 1 matrix. So our equality here is true. Now, if you've never multiplied matrices before, what we're going to do is anticipate this product over here on the right side is going to be a 2 by 1 matrix. So to get the result in row 2, column 1, I'm going to take row 2 times column 1. So I would multiply 4 times x1 to get this, plus 2 times x2 to get this. So that's going to be one entry over there on the right side. Then once I have the entry in that spot, I'm going to find the entry in row 2, column 1. To do that, I'm going to multiply row 2 by column 1 here. So we have negative 3 times x1 plus negative 1 times x2 to get this side. So we have expressed this system in matrix form, but we are going to condense it down to a little matrix equation. So we're going to say that x bar represents the column vector x1 and x2. This is equal to a matrix that we're going to call P times x bar, and I forgot my prime over here. So x bar prime equals P times x. So this equation represents the matrix form that we have over here, which is another way of writing this system. Now let's talk about when we use matrix notation, how do we express and verify solutions? So in example B, we're going to verify that x1 equal to 2e to the t and negative 3e to the t, and x2 equal to e to the 2t and negative e to the 2t are solutions to the system. Keep in mind here, we're just looking at a different way of expressing the solution to the system. Previously, we would have said this is an ordered pair solution, 2e to the t and negative 3e to the t. We've just now written it as a column vector. Same thing over here. We would have said this is another ordered pair of solutions, e to the 2t and negative e to the 2t. But now we have expressed those ordered pairs as 2 by 1 column vectors just because we have that versatility of notation. Now, I want to point out something that is guaranteed to confuse when you get to your homework. What we have right here is a column vector. Notice the bold print. So if I were going to write that by hand, I would use my matrix hat. We have our first solution, x sub 1. Remember, my dependent variables to the system were called x sub 1 and x sub 2. So this vector, x sub 1, contains a value for x1 and x2. So this x1 is different than this x1. The one that is in bold print, or as by hand we would write with a vector hat, this just means this is one particular solution. Okay, same thing here. We have x sub 2 in bold. That means this is my second particular solution, but this column vector contains a value or a function for x1 and a function for x2. So this x2 is different from this x2. Okay, so really what we have here is a first solution and a second solution, and each solution contains a function for x1 and x2. Okay, it's my job to confuse, I know. Now, let's look at verifying that these two solutions actually solve the system. We're going to do this by substitution. So I'm looking at my matrix equation, and I want to show that this first solution, x sub 1, verifies that equation. So I need to verify this by substitution. So on the left side, we're going to check x1 first. On the left side of my matrix equation up here, I need to find the first derivative of each entry. So the first derivative of my first entry is 2e to the t, and the first derivative of the second entry is negative 3e to the t. That was not too difficult, right? We want to show that this balances the equation, so I'm testing the equality here, which is equal to the coefficient matrix times the original variables, right? So I'm going to plug in 2e to the t and negative 3e to the t. Keep in mind, this side is x bar, this is x bar prime. They just happen to look exactly alike. So to see if this is actually a solution, I'm going to carry out the multiplication on the right side. And let's go over multiplication of matrices again. This one is a 2 by 2 matrix, 2 rows, 2 columns. This one has 2 rows and 1 column. So we know that our product must be a 2 by 1 matrix. So I'm going to anticipate that this result is going to be 2 by 1. Let me make it a little bigger here. 2 by 1. So to get the result in row 1, column 1, I'm going to multiply the entries in row 1 by the entries in column 1. So we're going to take 4 times 2e to the t. That gives me 8e to the t. And I'm going to add it to 2 times negative 3e to the t. That's negative 6e to the t. Okay, to get the entry in row 2, column 1, let me switch colors. We're going to go from row 2 times column 1. So I'll take the first entry, negative 3, times 2e to the t. That gives me negative 6e to the t. And then I add it to negative 1 times negative 3e to the t. That gives me 3e to the t. Let's go ahead and simplify to obtain 2e to the t and negative 3e to the t. So notice that's what we had on our original left side. We have verified the equality. So we know that x sub 1 bar is a solution. It checks out. Okay, let's check the second one. So for our second equation over here, we have x sub 2 listed as a column vector right here. And we're going to plug it into our matrix equation up here. So on the left side, we need the derivative of that column vector. So the derivative of this column vector is 2e to the 2t and negative 2e to the 2t. So we found the derivative on this side, and we're going to test and see, is this equal to the coefficient matrix times the original solution, the original x, right here we have original x, e to the 2t and negative e to the 2t. So let's carry out our matrix multiplication. We already know this is going to result in a 2 by 1 column vector. So we're going to take, to find the entry in row 1, column 1, we're going to take row 1 times column 1. We're multiplying corresponding entries and adding together. So we have, moving across the row this way and down the column this way, we have 4 times e to the 2t. That gives us 4e to the 2t plus 2 times negative e to the 2t. That's negative 2e to the 2t. Then to figure out the result in row 2, column 1, that is row 2, column 1, we're going to take row 2 of the first matrix times column 1 of the second matrix. We have negative 3e to the 2t plus negative 1 times negative e to the 2t, that's plus e to the 2t. Then we will simplify to obtain 2e to the 2t negative 2e to the 2t. And if I take a peek back over here, what we had on the left, we have verified the equality there. So both of those solutions, x sub 1 bar and x sub 2 bar, or those two column vectors, represent two distinct solutions to our first order system. Again, our goal here is just to learn the same problem with new notation. If you need some extra help with matrix operations, there's plenty of information in your textbook. You can go through and read about multiplying matrices, finding determinant of matrices, finding transposes of matrices. That is all there, and you may have some experience with that from previous classes. Now, let's take what we know from section 2.2 about superposition and linear independence and apply this to systems of differential equations. Part 2, theory of homogeneous systems. A, principle of superposition. Theorem, let x sub 1, x sub 2, and x sub n be n solutions of the homogeneous linear system x prime equals p of t times x on the open interval I. So I have n different solutions of my linear system, and each of these are n by 1 column vectors. Okay, they're n by 1 matrices. You hear that in Calculus 3 as column vectors. That means the same thing. It's just a matrix with one column. So these are n by 1 matrices, and we have n different solutions. Okay? Then the linear combination, notice regular x, no subscript, x of t equals c sub 1 times x1 of t plus c sub 2 x sub 2 of t up to c sub n x sub n of t, where the coefficients c sub I are elements of the real numbers for all I. That is also a solution. So this should remind you again of finding linearly independent solutions to a differential equation. If we have a solution to a differential equation, multiple solutions, then the linear combination of those solutions is also a solution. So that's exactly what this is saying. We're just recognizing we're applying this to a whole matrix or a whole system of differential equations as opposed to a single. So for example, from example 1, the previous system we were working with, we want to show that the linear combination x equals c sub 1 x1 plus c sub 2 x2 is also a solution to the system. So first, let's go ahead and form our linear combination. So x of t equal to c sub 1 times x1 plus c sub 2 x2 can be written as constant c sub 1. Now I'm just going to go back up here and pick up the elements of x1, 2e to the t and negative 3e to the t. Plus c sub 2 times my second solution. Remember the bold print x2 is just pointing me to the second solution. That was e to the 2t negative e to the 2t. So let's carry out these operations and simplify. So one operation on matrices here is scalar multiplication. I'm multiplying a scalar or a real number times a matrix. The way to carry that out is simply to multiply each element in that matrix by the scalar or by the constant. So it kind of feels like we're distributing that C1. We're going to do that for the first matrix and also for the second matrix. Okay, now we are adding matrices. When you add matrices, both matrices have to be exactly the same size. It's different than matrix multiplication. And the sum of the two matrices is going to have the same size as the two original matrices. So we're adding two 2x1 matrices. Our result is going to be also 2x1, 2 rows and 1 column. When we add matrices, we simply add corresponding components. So I'm going to take row 1, column 1 plus row 1, column 1. This looks like 2 c sub 1 e to the t plus c sub 2 e to the 2t. And then I'm going to add row 2, column 1 to row 2, column 1. We end up with negative 3c sub 1 e to the t minus c sub 2 e to the 2t. So we have this new vector. Please understand this is 2 by 1, 2 rows and 1 column. I know it sort of looks like a 2 by 2 matrix, 2 rows and 2 columns, but we have 1 entry in each row. This is a single entry in column 1. This is a single entry in column 1. So this is a 2 by 1 column vector, not a 2 by 2. So we have found this linear combination. Remember, each individual column vector on its own was a solution. That's what we proved up here. Now we want to show that this linear combination is also a solution. So we want to show next that x prime, let me switch colors again. We want to show that x prime equals p times x. So let's start by finding x prime. So I'm looking at this matrix and I'm going to find the first derivative of each entry. I might need some more room. So here's x prime. Differentiating term by term, we have 2c sub 1 e to the t plus 2 c sub 2 e to the 2t. Differentiating our second entry, we have negative 3 c sub 1 e to the t minus 2 c sub 2 e to the 2t. So there's the derivative of our solution on the left side, and we're going to find out, is this equal to the coefficient matrix? I'm using the same coefficient matrix as I had up here, 4, 2, negative 3, negative 1. And now we're going to plug in x, our linear combination that we just formed over here. 2c sub 1 e to the t plus c sub 2 e to the 2t, negative 3 c sub 1 e to the t minus c sub 2 e to the 2t. So I need to carry out the matrix multiplication on the right to verify the equality. So let's observe, since we're multiplying matrices, the coefficient matrix has 2 rows and 2 columns. The column vector of solution has 2 rows and 1 column. So the product is going to be 2 by 1. And that's good because over here I have a 2 by 1 column vector. So anticipating that the result is 2 by 1, we're going to have 2 rows and only 1 column. So to get the entry in row 1, column 1, I'm going to multiply row 1 by column 1. We're going to have a lot of distributing to do here. So I'm going to take the first entry in row 1 and multiply it by the first entry in column 1. So this is 2 c sub 1 e to the t plus c sub 2 e to the 2t. Then I'm going to add that to the second entry in row 1 times the second entry in column 1. So we have 2 times negative 3 c sub 1 e to the t minus c sub 2 e to the 2t. And we'll carry out that multiplication here in a minute. Okay, moving on to row 2, column 1, we're going to multiply now row 2, that's row 2 times column 1. So we're going to get row 2 entry, negative 3, times column 1 entry, 2c sub 1 e to the t, plus c sub 2 e to the 2t, plus the second entry here, negative 1 times the second entry here, negative 3 c sub 1 e to the t, minus c sub 2 e to the 2t. We're not learning a whole lot of differential equations here. We're learning linear algebra. Linear algebra is a pretty simple class, and it's one of the most useful classes as far as being able to manage a lot of information. You can have linear algebra for algebraic systems or for systems of differential equations. So our goal is to make sure that our two sides match. So I'm a little bit out of room, so I'm going to do the algebra above what I have here. We have 8 c sub 1 e to the t, distributing here and here, plus 4 c sub 1 e to the 2t, minus 6 c sub 1 e to the t, minus 2 c sub 2 e to the 2t. Okay, carrying out the distributive property in the second entry, we have negative 6 c sub 1 e to the t minus 3 c sub 2 e to the 2t plus 3 c sub 1 e to the t plus c sub 2 e to the 2t. Let's combine like terms and see if we have a balanced equation. Combining our e to the t terms, we have 8 c sub 1 minus 6 c sub 1, and that gives me 2 c sub 1 e to the t. And combining terms here, 4 c sub 1 e to the 2t minus 2 c sub 2 e to the 2t, that gives me 2 c sub 2 e to the 2t. It looks like I have, that's supposed to be a c sub 2 right there. Okay, so the first row matches. Let's make sure our second row matches. Negative 6 c sub 1 e to the t plus 3 c sub 1 e to the t. That gives me this term right here. And finally, negative 3 plus 1 gives me negative 2. So we do have a balance here. Sorry for the mess. I'm still learning how to use this right on surface tablet and didn't have enough room to show all the work there, but I hope that you can see the equality. We have showed now that each individual column vector was a solution on its own. We showed that up here in example 1. And now we have also shown, even though it was a little bit messy, we showed that the linear combination also solved the system. Now, how do we know when we have the general solution? Well, is there missing information? Is there an x sub 3 that I could anticipate that would add to my general solution? The way that we're going to tell is by using the concept of linear independence. And again, we studied this in section 2.2 for single differential equations. So let's remember the definition of linear independence. The vector-valued functions, x sub 1 of t, x sub 2 of t, up to x sub n of t, vector-valued functions, these are column vectors or n by 1 matrices. They are linearly dependent on some interval I, provided there exists constants c sub 1, c sub 2, up to c sub n in the real numbers, not all 0, such that the linear combination c sub 1 x1 plus c sub 2 x2 up to c sub n x sub n equals 0 for all t in I. That should be the bold 0 vector right there. So if I can form a linear combination, and I'm not using the trivial combination where all of my c's are 0, that is 0x1 plus 0x2 plus 0xn, that would give me clearly a 0. So I'm finding a non-trivial linear combination. Not all of those coefficients are 0, but it is equal to the 0 vector. Then that means they are canceling out. One is a scalar multiple of the other, is another way to think about it. If one solution can be multiplied by a scalar to look exactly like another solution, then they are scalar multiples of each other or they are linearly dependent. Otherwise, if the only linear combination that produces the 0 vector is the trivial solution, that is all coefficients c sub 1 are 0, then they are linearly independent. So what's a quick and easy way to test for this? If you have a lot of different solutions with many dependent variables. How do you tell quickly if you have linearly independent solutions? Well, like we did in section 2.2, we can use the Wronskian. The Wronskian is going to be just a little bit different when you have a system. The Wronskian, hopefully you'll remember, is a determinant, right? Suppose x sub 1, x sub 2, x sub n are n solutions of the matrix system. X prime equals P of Tx on I. Notice we are dealing with a homogeneous system here. Then two cases. Number one, if x sub 1, x sub 2, up to x sub n are linearly dependent, then their Wronskian is going to be 0 for all t on that interval. That interval may be negative infinity to infinity, or it may be some subset of that. So if the Wronskian is 0, we're going to conclude linear dependence. If those functions are linearly independent, then the Wronskian is independent of 0. That's how I like to remember it. Equal to 0, it is dependent on 0. Different from 0, it is independent of 0. So we will tie linear independence in with a linear combination, or the superposition principle, to conclude eventually that we have a general solution. For now, let's get to know the Wronskian for a system. Use the Wronskian to determine if x sub 1 and x sub 2 are linearly dependent or independent. Notice these are the two vectors that we've been working with. So we're going to use the Wronskian. Now, just by looking and using your intuition, do you think that those two vectors are dependent or independent? Did you say independent? If you said independent, you would be correct, because neither of those is a scalar multiple of the other. Notice the exponents on the e's are different in each spot, so these are going to be linearly independent. But let's show that with the Wronskian. So we're going to find the Wronskian of x sub 1 and x sub 2. Okay, the way we set this up, this is the determinant. We're going to put x sub 1 entries here and x sub 2 entries here. Remember when we found a Wronskian in section 2.2, we had to find derivatives? That's not the case when you've got column vectors. Now we have this little 2x2 determinant to calculate, so we're going to find our forward diagonal product, and then we're going to subtract our reverse diagonal product. Since we have a difference here, the order is important, so make sure you get the order correct. So our forward diagonal product is going to be negative 2e to the 3t. Remember, we're multiplying like basis, so we add the exponents. We get negative 2e to the 3t minus negative 3e to the 3t. So simplifying, we end up with e to the 3t. Think about the graph of e to the 3t. It's an exponential function. It has a horizontal asymptote on that x-axis. That means it's never going to be equal to 0 for its entire domain, for all t in negative infinity to infinity. So since the Wronskian is different from 0 for all t between negative infinity and infinity, that means this function here never equals 0. Then we can say x sub 1 and x sub 2 are linearly independent. So since the Wronskian of x sub 1 and x sub 2, check your notation, make sure you get vector hats on those x sub 1 and x sub 2. Since the Wronskian is different from 0 for all t, then we can say x sub 1 and x sub 2 are linearly independent. So here's what we know so far. X sub 1 and x sub 2 on their own, back up here, on their own we showed that each one was a solution to our system of differential equations. Then we made a linear combination of those same two solutions on example 2, and we showed, hey, the linear combination of those two vectors is also a solution. Now we've taken a little bit further and we've showed that they satisfy a particular property. In example 3, we saw that x sub 1 and x sub 2 are linearly independent. That means they code unique information. So this leads us to the conclusion about finding the general solution to a homogeneous system. Theorem, let x sub 1, x sub 2 up to x sub n be n linearly independent solutions, sorry for the misspelling there, solutions of the homogeneous linear system x prime equals p of t x on I where p of t is continuous. Then any solution, notice no subscript here, just general x, of the system can be written as a linear combination of the n linearly independent solutions x of t equals c sub 1 x sub 1 plus c sub 2 x sub 2 on and on and on up to x sub n. So we know that if each column vector is a solution on its own, then the linear combination is also a solution. On top of that, if we know that those individual solutions are linearly independent, then the linear combination is the general solution. That means I am not missing any information. I can't add any function to add further information to that system. So in example 3, explain why the solution given in example 2 is the general solution given in example 1. So back here, we showed that x sub 1 and x sub 2 are linearly independent. And up here, we showed that their linear combination was a solution. And we know that on their own, they are a solution. So here's how we put it all together and make our conclusion. Since x sub 1 and x sub 2, make sure you get your vector hats there, are linearly independent solutions to the given system, then x bar equal to c sub 1 x sub 1 plus c sub 2 x sub 2 is the general solution to the system. Hopefully you understand that linear independence, superposition, general solution, all of this relates back to what you know about individual single differential equations. We're now just applying it to a system of solutions. And one more time, I want to stress so that you don't get confused that x sub 1 bar is a matrix column vector containing a function for the variables x1 and x2. And x sub 2 bar is a column vector containing functions for x sub 1 and x sub 2. So be sensitive to the notation. If it has that vector hat, that represents a column vector, meaning the subscript just indicates this is my first solution. Okay, but it has a value for both x sub 1 and x sub 2, the dependent variables of the system. If, again, I've got the vector hat with the subscript 2, this just means, hey, I found a second solution, and it contains a value for both dependent variables of the system. Okay, let's take it one step further, and let's turn this into an initial value problem. Example 4, find a particular solution of the system from example 1 given x of 0 equals 0, 2. So notice no subscript here. Notice the bold print. This means we're dealing with a vector, a column vector. The input is the independent variable t, and the output is a value for the dependent variables. So the way I interpret this notation, this means x sub 1 of 0 equals 0 and x sub 2 of 0 equals 0. So those are my two initial conditions coded together in a single matrix equation. So let's go back and revisit our general solution. It was c sub 1 x sub 1 plus c sub 2 x sub 2. This was c sub 1 times our first solution, which was 2e to the t negative 3e to the t. Same system as example 1, same two solutions. And plus c sub 2, it was e to the 2t and negative e to the 2t. Okay, so let's make sure we understand how this represents a system. I have a single matrix equation here, but it represents a system. So this means x sub 1 is 2c sub 1 e to the t plus c sub 2 e to the 2t. And x sub 2 is negative 3c sub 1 e to the t minus c sub 2 e to the 2t. So I'm recognizing that this column vector right here has two components. Row 1 is x1, row 2 is x2, and it's equal to the linear combination over here on the right side. So notice I have a function of t for my first dependent variable and a function of t for my second dependent variable. So now we're going to apply our initial conditions. You can either do this in matrix form or you can do it in a separated form like what we have right here. So applying our initial conditions, our first one we can see is x sub 1 of 0 equals 0. So I'm going to set x sub 1 equal to 0, and I'm going to plug in 0 for t. This leads me to the algebraic equation 2c sub 1 plus c sub 2. Our second initial condition, x sub 2 of 0 equals 2. So now I'm going to set x sub 2 equal to 2, and I'm plugging 0 in for t. That leads me to the algebraic equation 2 equals negative 3c sub 1 minus c sub 2. So together here we have an algebraic system that I need to solve for c sub 1 and c sub 2. You can solve that by substitution, you can solve that by elimination, or you can even put those in a matrix and let your calculator do the work for you to reduce the matrix. If you plug it into your calculator and reduce the matrix, you will end up with negative 2 and 4 as the solution. So c sub 1 and c sub 2 are equal to negative 2 and 4. So we're ready to go ahead and express our particular solution. Following this pattern over here, we can say x bar of t is equal to c sub 1 negative 2 times x1 2e to the t negative 3e to the t plus c sub 2, which is 4, times x sub 2 e to the 2t negative e to the 2t. Now if we want the interpretation of what this matrix equation represents, we can write it in terms of two distinct solutions. X bar is a column vector containing two elements, x sub 1 of t and x sub 2 of t. X sub 1 is row 1 all the way across the equation. So multiplying, we have negative 4e to the t plus 4e to the 2t. And multiplying across row 2, we have 6e to the t minus 4e to the 2t. So those are our two solutions in individual form, and here's what it looks like in matrix form. The only thing we lack for this section is solutions to non-homogeneous systems. Let x sub p be our particular solution to dx over dt equals p of t x plus f of t on I, where p of t, the coefficient matrix, and f of t, that's the non-homogeneous term, are continuous. Let x sub 1, x sub 2, up to x sub n be linearly independent solutions of the associated homogeneous equation on I. Now, if those are linearly independent, then we know their linear combination forms the general solution to the associated homogeneous equation. For the non-homogeneous equation, we get this extra term called the particular term. This side is called the complementary function, x sub c, and this one is the particular function, x sub p. Notice the arbitrary constants go with the complementary function. Those can be determined with initial conditions, and x sub p does not have an arbitrary constant associated with it. Example 5. Consider the system written here. This is a first order system in 3 dependent variables, x sub 1, x sub 2, x sub 3, and the independent variable t. We want to express this system in matrix form, identifying x prime, p, x, and f of t. So in matrix form, we begin by writing the left side of the system as a column vector. It's going to contain the components x1, 2, and 3, and we need to find the first derivative of those components. Next, we're going to identify the coefficients of x1, x2, and x3. This is called our coefficient matrix, and in this case, we have constant coefficients. So what I'm doing here, in column 1, we have coefficients of x sub 1. In column 2, we have coefficients of x sub 3, x sub 2, and in column 3, we have coefficients of x sub 3. So that's our coefficient matrix times our column vector of variables, x sub 1, 2, and 3. And then we're going to add our non-homogeneous terms out here in a 3 by 1 column vector. So in this matrix equation, we have x bar prime on the left side. We have our coefficient matrix P times x bar plus a column vector of non-homogeneous terms. So both of these represent the same system. You can see this one's very efficient and concise. This one organizes our information into different components, but they both represent the same system. To finish off, we're going to assume a solution x sub c of t. Now remember, we're not solving the system, we're just getting to know the notation. So if we'd gone through the process and we found this as our complementary function, notice the arbitrary constant, c sub 1, 2, and 3. We could determine those with initial conditions. And a particular term containing functions of t that's going to satisfy the non-homogeneous part of the system. Show that x of t equal to x sub c plus x of p is the general solution to the system. So let's fill in the details for our general solution. Our general solution, x bar, is the sum of the complementary function plus the particular term. X bar represents the 3 variables of the system, x sub 1, x sub 2, and x sub 3. This is equal to the sum of our complementary function plus our particular term. So I'm going to add those all together in a 3 by 1 column matrix. Now I'm going to pause the video to do this, and I'll be back in a split second. All right, that was quick. You can see I've taken the terms of x sub c and tacked on the term x sub p there on the end. So x sub p terms are there in red for you to see. So that's what our general solution looks like. Now we have to verify that this is the solution to the system. So we want to show that it solves our matrix equation that we have written up here. So I'm going to rewrite this equation down below so I can have it for reference. There we go. Now let's test for balance. So I'm going to take our solution and plug it into our matrix equation. So let's find the first derivative of our general solution up here. So I need the first derivative of these terms here. So finding the first derivative, row by row and term by term, we end up with something like this. Notice I'm just differentiating each term with respect to t. And the last line, okay, so we took our general solution and we plugged it in right here, and we have now found that derivative. So we're going to test and see, is this equal to the right side of our matrix equation? So let's fill in our details here. We've got our coefficient matrix. In this case, we have constant coefficients. It's possible eventually that those are functions of t. Let's fill in the information for x1, x2, and x3 from our general solution. And then finally, we have our non-homogeneous term. So to see if this is a true equation, we need to carry out the matrix multiplication and addition. Notice in our matrix, we have a 3 by 3 coefficient matrix times a 3 by 1 column vector. The middle two dimensions match, so the matrix product is defined, and the result will be a 3 by 1 column vector. So we can anticipate the result here to be a 3 by 1, 3 rows and 1 column result. Now, let's carry out our matrix multiplication. So to get the entry in row 1, column 1, I'm going to take the values of row 1 of the first matrix and multiply them by column 1 of the second matrix, multiplying corresponding entries as we go. So we're going to start and multiply 3 by the first entry in column 1. So multiplying each coefficient by 3, we end up with 6c sub 1 e to the t plus 6c sub 2 e to the 3t plus 6c sub 3 e to the 5t plus 9t. Next, I'm going to take the second entry in row 1 times the second entry in column 1. Multiplying by -2, we obtain -4c sub 1 e to the t plus 4c sub 3 e to the 5t minus 10. And finally, we're going to take the last entry in row 1 times the last entry in column 1, and that one's easy. We get a 0. Now, let's work on our second component. So now we're working on row 2, column 1. So we're going to take the entries of row 2 times the entries of column 1. So I'm going to take the first entry in row 2 times the first entry in column 1. So I'm multiplying each one of those terms in row 1 over here, column 1, by -1. Then we move on to the second entry. 3 times the elements in the second row here. We get 6c sub 1 e to the t minus 6c sub 3 e to the 5t plus 15. Finally, the last entry in row 2 times the last entry in column 1. We have minus 2c sub 1 e to the t plus 2c sub 2 e to the 3t, running out of room, minus 2c sub 3 e to the 5t minus 4t. And then in our last spot here, we're going to take the entries of row 3 times the entries of column 1. Get some space here. So the first element is easy. 0 times the first element in column 1 goes away. -1 times the second entry would give us -2c sub 1 e to the t plus 2c sub 3 e to the 5t minus 5. Then the last spot times the last spot here. We have 3c sub 1 e to the t minus 3c sub 2 e to the 3t plus 3c sub 3 e to the 5t plus 6t. Okay, so that's a 3 by 1 column vector. And then notice I'm going to add to that another 3 by 1 column vector. So I'm going to go ahead and tack those on to this step. Row 1 gets added to row 1. Here we have another 7t minus 15, and here we have a minus 6t plus 7. Our last goal here is to simplify and to make sure the left side is equivalent to the right side. So next we're going to combine like terms. So let's take all of the coefficients of e to the t and combine them. In row 1 we have 6c1 minus 4c1. That gives us 2c sub 1 e to the t. Coefficients of e to the 3t, looks like we just have one, so 6c sub 2 e to the 3t. And coefficients of e to the 5t, we have 6c sub 3 plus 4c sub 3. That gives us 10c sub 3 e to the 5t. Looks like our 9t's cancel out. We have negative 10 plus 13, which is plus 3. So notice row 1 on this side of the equation matches row 1 on this side of the equation. So far, so good. Let's test our second row. I'm going to add coefficients of e to the t first. We have negative 2c1 plus 6c1, so we're up to 4c1. 4c1 minus 2c1 gives us 2c1 e to the t. Next, we'll combine coefficients of e to the 3t. Negative 2c2 plus 2c2, so that cancels out. And then we'll combine coefficients of e to the 5t. Negative 2c3 minus 6c3, that's negative 8. Minus 2 more gives us negative 10 c sub 3 e to the 5t. Combining our non-homogeneous terms, let's see. We have negative 3t minus 4t, that's negative 7t plus 7t, all that cancels, and the 15 and negative 15 cancel. So row 2 here looks like row 2 here. We're almost there. We've got one more line to check. Combining coefficients of e to the t, we have negative 2c1 plus 3c1. That gives us c1 e to the t. Coefficients for e to the 3t, looks like we just have one term here, minus 3c sub 2 e to the 3t. Combining coefficients of e to the 5t, we have 2c3 plus 3c3. That gives us 5c3 e to the 5t. And the variable terms cancel, and we have minus 5 plus 7, which is plus 2. So this matches this. We can say, therefore, x bar is the general solution to the system. So your goal in this section is to learn the notation and maybe even to learn some matrix operations. If you're unfamiliar with those matrix operations, there is more information in the text about multiplying matrices, adding matrices, finding the transpose of a matrix. You're welcome to check that out. Next time, we'll actually solve some systems.